I think today there are two lectures. So in between we have. Can you hear me? Can you hear me now? Hello? Can you hear me clearly?
Yes, sir. You're clear. You're clear, sir.
Okay, it's clear. Is that right? Okay. So I think today we are going to talk about chemical looping, ammonia synthesis. Um, so I think in the literature they abbreviate this process and call it CLAS. If you read the literature, they basically call the clause or the CLAS, CLAS. So I think that in the last week I have lectured different method of the making ammonia. So one of it is chemical looping. At that time, I did not specifically say clearly what chemical looping ammonia synthesis is. It's really high level. So today I'm going to talk about a very detailed chemical looping. So actually, my group has been doing a lot of the chemical looping research using microwave and also microwave plasma. And also I'm going to show you other people's work. So that's our focus today. Um, can you see my slides here?
Yes, yes, sir. It's coming.
Okay, it's clear. So here's today two sessions. We are going to talk about the history of chemical looping in general. First, chemical looping in combustion, and but that's how the chemical looping started. Then later on, and the chemical looping has been utilized in ammonia synthesis. So I'm going to talk about in ammonia synthesis uh, two the different approach. One is the conventional thermal heating versus the microwave heating. So you can see the differences. And also, at the end, I'm going to talk about microwave plasma in chemical looping. So they are different things. So I hope we have time to cover all of these topics for today. But I'm going to ask the questions since there's a small audience now. I want the audience to speak up every time when we talk about different topics. Otherwise, if I keep on talking without feedback, it's very difficult to talk. So I'm going to ask the audience from time to time today throughout my lecture today. Okay. Mm. So here's the history. Let me write it down.
Yes, sir.
Yeah, you can. I'm going to write it down. No, history. So history of chemical looping in general. So how the chemical looping started? Well, chemical looping started try to do the air capture. Okay, so here's the uh, natural gas combustion. I know in many other part of the world, you don't use the microwave for combustion. You use um, use the coal. But I want to use the gas. In the United States, most of combustion in chemical plant, they use the natural gas, like a natural gas fired heater and combustion. For example, mm, so if you go to petroleum refinery, so you can see my highlight, all right? So pretty much the natural gas, the fired heater are very popular in refineries. So what they do is and then methane plus the air and form hydrogen, CO2, and nitrogen, and then they and then produce a heat. So and also this is for power generation. and also for power generation. So now they come to the quiet. Okay, for power generation as well. Basic combustion is for the power generation. Now the for the CO2 capture, so the in from the combustion gas, so the carbon dioxide is about 8 to 15%. The reason being that if you look at the combustion of formulation and then the methane plus air, what's in the air? There's most of nitrogen, all right? So you consume the oxygen and then the still nitrogen left over. So if you look at do the calculation and then the carbon dioxide concentration 8 to 15%. So CO2 capture require 1200 psi, which is 82 bar, is needed for the pure CO2. So I'm asking question, okay? Before I go to the next one. Okay, read my question, and then I want audience answer. I'm going to the so here's here's question. Okay,
Yeah.
you know the CO2 capture from combustion gas. Combustion gas contains 8 to 15%, and then the CO2 capture needed 1200 psi is needed for pure CO2 because that means if you capture CO2, make it pure, which is the 100% CO2, even that you need 82 bar pressure, and then the question is why do you need CO2 capture from combustion capture to make it 100% from combustion flue gas? You know what I'm saying? So why you have to purify the CO2 and then capture it? What can anybody tell me? Why don't you shoot? Why can't you shoot the flue gas into the ground?
Yeah.
Go ahead, ask question. Why can't you?
We need to capture CO2 100%, then only you can minimize the carbon footprint. And then if we talk about colors about emission, green, blue, turquoise, orange, gray, so everything based on carbon footprint. So if 100% CO2 is captured, then it's coming under blue category.
Okay. Yeah, well, it's really come to the I think that's very very good answer. So why do you have the need CO2 capture to make it 100% from combustion flue gas?
So
why can't you inject the flue gas directly into the ground? You can inject. You don't have to capture. You can inject directly into the ground. That's the second question.
CO2 is one of the global warming gas. So it's one of the greenhouse gas. It will give the global warming effect.
Yeah. Okay. So basically, if you look
at you are talking about recirculating the flue gas.
Sir,
Yeah, go ahead.
this is for only the ammonia production, sir.
No.
No, this has nothing to do. This is basically I'm talking about before I talk about ammonia, I'm talking about history.
Okay, sir. Actually,
Okay.
CO2 we want to remove due to for avoiding the global warming, as well as if next one is injector focus.
Okay.
Actually,
So looks like okay. Let me. I think I'm moving too fast now. Okay. Let me go back. Okay. So here's the topic today. Okay. Let me go back. Okay. So. Yeah, I think I go too fast because I assume you know the topic. So let me go back. Okay. All right. So here's the outline of today's lecture. Since you're asking questions, first I'm going to talk about the history of chemical looping in general. Has nothing to do. So at this point, when I talk about history of chemical looping in general, it has nothing to do with ammonia. Then I'm going to talk about chemical looping and combustion. Okay. At this time, second bullet has nothing. Okay. So talking about combustion has nothing to do with ammonia. The third point. Now,
sir, snacks actually. Snacks are some getting on cutlets.
okay, so let me repeat today's outline. Okay, so today's outline, and I'm talking about the history of chemical looping. It has nothing to do with ammonia when I talk about. That's what next. Then I'm going to talk about chemical looping combustion, and then the third bullet. Then I will show chemical looping ammonia synthesis. I'm going to introduce how the how the researcher utilize the chemical looping concept for ammonia. So only until this point, we are talking about ammonia. The first two bullets has nothing to do with ammonia. So once you understand how the chemical looping in combustion, you should understand the yellow portion. The last part is the microwave plasma in chemical looping. Do you understand the outline of today's lecture? Can anybody say something? Okay, is that clear? All right. Okay, so next slide, I'm going to talk about chemical looping in general. Again, it's just concept. It has nothing to do with ammonia. Later on, you will see ammonia. So I want to make sure you understand the theory behind the chemical looping before we move on to ammonia. Okay, ammonia is not combustion. Okay, so all right. So if you understand the topic clear, so I'm going to start. Any questions? Go ahead.
No, sir, you can continue, sir.
Can we continue?
Yes, sir.
Okay. All right. So let's say the history of chemical looping in general. Chemical looping, it came from the combustion. So natural gas combustion, for example, the fire heaters, it undergoes this is the chemistry. Okay, so basically methane plus air, and then from CO2 and the water and the nitrogen, and then and also this the combustion also for power generation as well. So here's the fact. CO2 capture from combustion gas. CO2 capture means okay. I think I need to go slow. I don't think the audience understand the concept. So the definition of CO2 capture means you need to purify flue gas from 15% to 100%. So CO2 capture, once you do the CO2 capture, you need a 1200 psi, which is 82 bar, is needed for pure CO2 injection. So everyone understand from the beginning, CO2 capture, the flue gas is 15%. You need to purify the 100%. Then you can inject the ground. So and then they need high pressure. You need 80 bar pressure. So that's why I have two questions. Why do you need a CO2 capture to make it 100% from combustion flue gas? Why can't you inject the flue gas directly into the ground? So why can't you inject this? Can you see the highlight here?
Yes.
Why you have to inject pure CO2? Why can't you inject the CO2, water, and the nitrogen, the mixture into the ground?
Actually, H2O and N2 won't affect environment, sir. H2O is actually water, and then nitrogen is actually exists in atmosphere. So only thing the CO2 contains carbon footprint that need to be avoided because it is the factor for global warming, as we mentioned earlier. And CO2 giving in LC analysis point of view, I mean the environmental point of view, global warming potential is measured by terms of CO2 equivalent.
Okay, so can you read the third question I'm typing now? Okay.
Inject pure CO2 to the ground. The case 82 was
82 bar, right? So that's the data. So how high the so how high the pressure you need?
Sir, one thing we want clarification, sir. Directly into ground in the sense, in that place you are mentioning ground means. Can you tell it brief, sir?
Do you understand the partial pressure concept?
Yeah, yes, sir. Partial pressure concept is also. Yeah.
So basically, you need 82 bar CO2 pressure. Now, if you inject the mixture, to make a CO2 into the liquid, because you have nitrogen there, nitrogen is not compressible, is that right? You cannot compress nitrogen by pressure. So you have to apply very high pressure, much more than 82 bar, to make CO2 into liquid if you have nitrogen present, because you need partial pressure of CO2. So this pressure will be very high. You're talking about 5,000.
Yeah, understand, sir.
You saw me? Okay, because you're dealing with a partial price of CO2, so you need high price. That costs a lot of money. Okay, 5,000 psi. That's a lot. I mean, it divide by 14.7. That equals a bar. Okay, so let me summarize. I'm glad that we have quite Q&A. So basically, if you capture CO2, make it 100%, that CO2, pure CO2, you increase the pressure 82 bar, you can inject into ground. It's called a CO2 capture and storage, put in the ground. You have to put a CO2 liquid into the ground, not in the gas phase. Okay, so that's called a storage. Now, if you don't purify CO2, you have CO2 and the water and nitrogen all together, and then your partial pressure will be very high, because CO2 need 82 bar, because the nitrogen, your concentration is only 8 to 15%, so you have to apply very high pressure in order to make CO2 into liquid in the mixture. You follow me?
Yes, sir.
Partial pressure.
Yes, sir. So expelling the CO2 from flue gas, what we understood means you want to segregate CO2 alone from flue gas.
Thank you. I like the word. I like the word segregation. Yes, you have to segregate, because otherwise, if you segregate, you need 5,000 psi, because you have to increase pressure in order to make CO2 partial pressure equals to 82 bar. You follow me?
Yes, sir.
Anybody can do a quick calculation? Hold on, let me. 5,000 psi, because in the United States we use the psi. I'm going to calculate 5,000 divided by 14.7. So 340 bar. So basically, so okay, if you don't separate the CO2 from the flue gas, you need a 340 bar. That's very high. So basically, okay, you say I'm going to shoot the flue gas into the ground, and then you need those 340 bars, and then under 340 bars, CO2 will become liquid. Then shoot the ground. Nitrogen is okay. Nitrogen is not compressible. You inject it, it will come out. So, but you need CO2 to be liquid in order to put the ground in storage. So anyway, so in order not, you don't want to do the 340 psi, because the operating cost and the equipment cost is so high, all right? So as a result, you have to selectively take CO2 out. That's why there's so many technology, and then remove the CO2 or make a pure CO2 before the inject in the ground. Do you understand this?
Sir, in which ground means you are mentioning as that directly? Ground
you have to inject it. Basically, that's called CO2 capture and storage, right? It's called
yes,
CCS, all right? CO2 capture and storage. You have to do the CCS, all right? So it's not just capture. You have to do storage. It's called the CCS, carbon dioxide capture and storage. So that means you have to purify CO2, and then only the purified liquid CO2 you put in storage. Otherwise, what do you do with that CO2? It's captured. So it's all together. CCS is all together.
Sir, one more question, sir.
Make sense?
Yeah, actually, mixture of CO2, H2O, and N2, If I compress it into 82 bar, then it won't, the CO2 would not segregate.
Yeah, that's true. Yep, the mixture 82 bar will not liquid. You need a 340 bar.
Okay.
Okay, so the pressure is too high. So that means you need to basically purify CO2. So how do you purify CO2? That's the next. Okay, at this point, I'm not talking about the ammonia. I'm just give you some theory of chemical looping. Again, today's topic is chemical looping for ammonia, but this is a very basic theory of chemical looping. You have to follow my thought on the CO2, and then you will understand ammonia. You follow me?
Yeah, yes, sir. Understand, sir.
Yeah, just follow, just stay with me, and then please understand CO2 capture, and then the oxygen carry next. Then you will understand how chemical looping has been applied for the ammonia synthesis.
That's why we are going with the absorption and desorption.
Okay. Yep. So basically, there's another approach to make the pure CO2 without nitrogen. So methane plus the oxygen. So basically, pure oxygen to make CO2 and water. The problem is most of the combustion in the chemical or refinery, they use air. If you use a pure oxygen to begin with, that's called oxy-combustion, not air combustion. And this oxygen costs a lot of money. So how to make the pure oxygen? It's called air separation. That means cryogenically you separate the oxygen from air, then use for combustion. So here's cost. If you, to say different way, if you use the oxygen in the methane combustion, and then yes, you can produce pure CO2 because the nitrogen never present, but this is going to be cost. Understand? It's a big.
Yes, sir.
Lot of cost. Okay. All right. So now you see the background. So now they come to the chemical looping combustion. It's a chemical looping combustion. Again, at this point, I am not talking about ammonia. I'm talking about combustion, chemical looping. Later on, I'm going to apply this chemical looping concept to ammonia. At this point, it's still combustion, okay? So this chemical looping combustion is called CLC. If you do the literature search, last 10 years, there's so many, you are talking about 10,000, maybe more than 10,000 papers in the open literature. So this concept of using oxygen carry to do the combustion. What's the idea for the combustion? Number one, remember, if you do the combustion to make a pure CO2, you have to make the pure oxygen. Okay, so chemical looping using. Let me back up. Okay, so if you want to produce a CO2 without nitrogen, you have to use the pure oxygen. All right. If you use air to do the combustion of methane, you produce CO2 and you produce nitrogen because nitrogen will never combust and then come together. So the invention of chemical looping is I am still using air, but I want to produce CO2. So this is the objective. The objective of chemical looping combustion is using air, but still produce the pure CO2. From the last 30 minutes discussion, we understand producing pure CO2 is important, all right? Because you have to do the CO2 storage, called carbon capture and storage. You need pure CO2. If you don't have the pure CO2, you have to apply very high the pressure. And to make CO2, into liquid in order to inject the ground, because the nitrogen is the dilute flue gas. So the invention of chemical looping process is the using air but still produce CO2. So that means the nitrogen and CO2, they do not see each other. I'm simplify this. So there's no need to separate CO2 from nitrogen. So understand? So nitrogen in chemical looping, nitrogen and CO2 do not see each other. There's no need to separate CO2 from nitrogen. In the regular combustion, CO2 and nitrogen, they see each other. You have to do separation. So I don't want to talk about how to separate CO2. There's the ammonia, there's amine, and a lot of the separation. So that's too much of the detail. So the objective of the chemical looping combustion is using oxygen carry. So and then objective is using air, but still produce the pure CO2. And then in order to do so, I mean, if we are successful, nitrogen and CO2 do not see each other. So there's no need to do the separation CO2. And there's no need to do air separation, because oxygen combustion so the oxygen combustion require expensive air separation. Okay, so by doing the chemical looping, we do not need no need to do air separation. Okay, so this cartoon really tell you how this thing is going to work. So basically, you need two reactor. Okay, so the first reactor is you begin with metal oxide, which is this for the combustion process. Instead of having methane react with oxygen, you react with iron oxide, so you form CO2, water, and pure iron. So iron and iron oxide, they are solid, so that they call oxygen carry. So by doing so, iron oxide turn into iron. You see the reduced iron coming to the other reactor. So reduce the metal means the iron come into another reactor. So if you look at on the fuel reactor on this side, here's the reaction. It's iron oxide plus methane forms CO2, pure CO2, water and iron. All right. So basically if you look at it's CO2 coming out from this side, there's no nitrogen. Where's the nitrogen? Nitrogen on this side. So the moving part is this is solid. So you have the metal, the iron oxide, which is a solid, turn into the reduced iron, and then you move reduced iron to another reactor, and then react with air. So that reaction is iron here plus air to form iron oxide and oxygen lean air. Oxygen lean air means this is basically the release it. Then the solid will come back. Solid, the metal oxide coming back. That's why they call it chemical looping. Do you see that? So you have two separate reactions. This is exothermic reaction. Okay. So this part is exothermic because you oxidize the iron. Oxygen reacted with the iron. This is highly exothermic. So this is the heat you want to generate. On this side, most of the time is exothermic, but it can be endothermic. Okay, so basically you want both reactions release the heat. That's why this is combustion. So if you look at both sides, air coming in, but the nitrogen coming from left-hand side, and then the CO2 from the other side. And then the differences compared to conventional is this looping the material. Is it clear? Before we move to the next ammonia, I want to make sure you understand that this chemical looping concept. Can anybody say something? Do you think this concept is clear to you?
Yeah. Yes, sir. We understand, sir, chemical looping and the importance of chemical looping. I have a doubt, sir, in combustion. Previous slide, we said
Yep.
oxy combustion. Before combustion, we can remove nitrogen from air
Yep.
and use oxygen alone. We can employ to complete the combustion reaction. So,
Yep.
in which, if it is pure CO2, then 82 bar are made for condensation or liquefaction. If it is CO2 and H2 mixture, then what would be the process, sir?
It's going to be basically you combustion the CO2 and water, so you need a so basically the CO2 and the water separation is very easy. Water, we know water is all right. If you drop the
Yes, sir.
so 25 degrees C, 1 bar. So the 25 degrees C, 1 bar. Water is liquid, correct?
Yes, sir.
So that means before you reach 82 bar, CO2 is in the gas phase. Only when you reach 82 bar, CO2 is gas phase, all right? But before that, water, long before the reach 82 bar, water become the liquid already. So you separate. Actually, by the way, it's a very good question. So I want you to make sure you can. I'm not trying to. So I think in the future, if we discuss if we have these courses, I want to have some very basic fundamental, maybe teach something about the general, I would say, it's called ChemCAD or some of the simulation knowledge in this class. Okay, so let me answer your question. Okay, so but that's a good question. Okay, so this is vessel. Okay, I'm gonna have a new slide answer your question. Okay, hold on. So I'm gonna show you water and the CO2 separation is very easy. Okay, it is the CO2 and nitrogen is very difficult. Yeah, I think if we teach this in the future, I think we need to have some kind of someone need to lecture just like what I'm doing, some kind of simulation tool. Then you can from the simulation tool you can see clearly, okay. So let's say you have CO2 and the water present here, and then let's say it's the ambient temperature. Okay. Okay. So 25 degrees C. Follow me. So now I'm increase the pressure. Okay. So okay. So now I'm increase the pressure now. So just follow me. So keep in mind at 1 bar, 25 degrees C, water is liquid, all right? So basically, by the time you increase the pressure, let's say maybe to 2 bar, what's going on here? So if you have a vessel, and then you increase the pressure at 25 degrees C with a mixture of CO2 and water at 2 bar 25 degrees C, what's the formation of water? It's a liquid, all right? Understand?
Yes, sir.
1 bar 25 degrees liquid, 2 bar water will stay in liquid anyway, all right? If you keep on increasing, what's at 2 bar 25 degrees C,
Yes,
what
sir.
is CO2? It's in gas phase, correct?
Yeah.
So
Anyhow.
can you
Yeah, yes, sir.
can you put a drain here? You just put a drain here, all right? It's gone.
Yeah. Yes, sir. Water will get condensed at room temperature itself.
Yes. So you just drain them out. Okay. You follow me? You just
Yes,
drain
sir.
them.
But
And then when you reach 82 psi, it's all CO2. So water and the CO2 separation is easy. Okay. That's why I say that the next year we will talk about it. You need a simulator. You put the simulator here, you will see. You put a gas phase, and then you will see the water come into condensed phase. The simulator will tell you easily. Okay. So basically, I would say water. Very easy. Okay. Now I'm changing. You agree, all right? CO2 and the water separation is easy because I can drain it. So now I'm changing. It's not water. I'm adding N2 now. So I'm adding N2 now. What's happening? You increase the bar even until 82 bar. What's going to happen? 25 degrees, 82 bar, water is gone, all right? And then you drain the water is gone, all right? Do you see the problem? CO2 and CO2 and N2 stay still in the gas phase. They are not separatable.
yes.
Make sense?
Yes, sir.
Okay. So this is the reason you need to keep on going to 340 bars. If you have if you go to 340 bars, what's happening was, if you go to the 340 bar, what's going to happen? If you go to 340 bar, N2 will be here. CO2 will be liquid phase. Liquid, you can separate, you can drain them, and then N2 in gas phase. So this line is called the phase. This line called the phase separation. Make sense?
Yeah. Yes, sir. If nitrogen.
Okay. Nitrogen is not compressible. Nitrogen at the room temperature is not compressible. You have to. It's not just the nitrogen separate nitrogen CO2. It's not by the pressure. It's cryogenic by the temperature. I think you need to go to minus 190 degrees C in order to make it into liquid. That's not doable. That's why you get the liquid nitrogen. All right. So anyway, so now you see the problem. All right. Every time you have nitrogen and the CO2 together, you have to have a very high pressure to separate them. So again, you do not want the nitrogen and CO2 to see each other. The moment that they see each other, that's the problem. 340 bar, that's a lot of high pressure. Okay. So is it clear now? Did I answer your question?
Yes, sir. Now clear, sir.
It's clear, all right? So now you know, I want everyone to read this, okay? The title is a chemical looping combustion. The concept of using oxygen carrier is the objective of the CLC chemical looping is using air, but still produce pure CO2. You understand what? I'm going to use air in combustion, but still produce CO2. There's no separation. So what's that? What's mean that? Nitrogen and CO2 do not see each other. There's no need to separate CO2 from nitrogen. So this chemical looping is really tell you how to do that. In order to do that, you need oxygen carry. Oxygen carry means is begin with the iron oxide on the right hand side, and then react with the methane, which is a combustion medium, form CO2. You see the process does not include nitrogen. It just oxidizes and make CO2 and water, and then release heat. Then the metal oxide becomes metal iron, and then you're moving solid into another chamber, and then the iron react with air. So at this time you can use air, and then form the iron oxide. See, this is chemical looping reagent has to come back. It starts from the iron oxide, making the iron and then oxidize, and then you can come back. That's why they call it looping. So by doing so, you release a lot of heat, because we all know to oxidize iron using air, you release a lot of heat. The heat energy is balanced. That means the whole process, the heat produced is equal. The whole process, the amount of heat produced is equal to here. So the chemical looping produces heat is equal to this reaction. You just separate the combustion into the two separate directions. So when you come back in the next lecture, I'm going to show you the picture of the chemical looping. The whole chemical looping is really engineering. Engineering means you have to move a solid around from the one vessel to another, one vessel to another. So one side you produce CO2, the other side you basically produce air. This is called the O2 depleted air. That means the nitrogen is on this side. So basically the N2 is on this loop. You see that? CO2 and the nitrogen, they don't see each other. We spent so much time today talking about you do not want the CO2 and the nitrogen see each other, all right? Because if you have CO2 and the nitrogen see each other, you'll be facing the problem here, because nitrogen CO2 separation, you need a 340 bar, too high. So yeah, that's a lot of work. Oh, you have to use the organic solvent to extract CO2 coming out, and then you have the different way to purify CO2, but just by pressure, the moment you have nitrogen and CO2 see each other, that's a problem. So that's why you have to pre-separate CO2. Okay. So then the chemical looping solve this problem. But the challenge of chemical looping is you have to move a solid around. So before we go to next, I want to make sure everyone's clear here. Do you understand what I'm saying here? Is it clear?
Sir, that reduction, if you do O3, return back to Fe, is it that much easy, sir? Compared to
Say it again.
Fe oxidation is fine, sir. Fe ion oxidation is fine, sir.
Yeah.
But ion reduction, it is not so easy.
Yeah, it's not so easy. So, well, you are right. It's not so easy. That's why the whole process is purely well, this reaction it can be done. You can as long as you increase the temperature to like I think the 800 degrees C, this ion reduction you can react with the methane. Yeah, it can be done. It's just a matter of temperature. You follow me? So iron oxide reduction by the natural gas, if you increase the temperature to 800 degrees C on this side, it can be done. This reaction will take place.
So the energy requirement for maintaining that 800 degrees centigrade.
Yeah, I think the whole process is not chemistry problem. So you are asking this reaction difficult. The chemistry already demonstrated. And then the chemistry here also demonstrated. I think the challenge here is engineering. So when I think after the break, and then when you come back, I will show you how complex is the process, the hardware on the oxygen air combustion. All right. So you have to move solid around. Let me put it. If you add these two equations together, this one and this one together, adding them together, the overall reaction is the same as this. So the amount of heat generated is the same from energy point of view. So if you're adding the two reactions together, it's the same. So we basically just separate this reaction into two loops, one using the oxygen carrier. Okay. So I want to make sure you understand here before I go to next, because next is not gonna now you have background information now, right? To do the combustion, I can use the oxygen carrier. So next, I'm going to talk about ammonia. Until this point, there's no ammonia. Okay. So next, I'm going to see how the same concept apply to ammonia synthesis using chemical looping. I want to make sure do you have any question here?
It's clear, sir. No?
It's clear? Okay,
Yeah.
Cool. Let's go to next. So again, I'm repeating. Until this point, I hope you understand the concept. Chemical looping concept or the theory and practice is originated from combustion. Okay, again, chemical looping is coming from the origin from combustion. Only last 5 years, researchers apply the chemical looping combustion concept to ammonia and chemical looping, but there's no oxygen carrier anymore. Here, you have an oxygen carrier, which is iron oxide. In ammonia synthesis, you need a nitrogen carrier. Now I'm talking about ammonia, okay? So that's why I keep on reminding you, don't be confused when I talk about combustion, because I want to make sure you understand the chemical looping concept, and then we apply to here. The concept of oxygen carrier, please read my title. So this is the reason I did, on day 2, when I introduced a different method of ammonia synthesis, electrochemical, microwave, plasma, chemical looping, I did not get into this detail. So today, I think this is really a focused topic. I'm spending time to talk about chemical looping because that's the Dr. Anand designed this topic. So I really have to, instead of giving you a superficial concept on chemical looping, so I give you the background of chemical looping in general in combustion. Now it's chemical looping in ammonia synthesis. It's a similar concept, but different carrier. Instead of oxygen carrier, obviously we need a nitrogen carrier. So let me, before we go to break, I have a lot of data here. So I want to ask a question. In methane combustion, we want to produce pure CO2, all right? We don't want the nitrogen and CO2 see each other because that affect pressure and CO2 capture, all right? That's all clear, all right? So, and then we do this the chemical looping. So I'm asking a question now, okay? So this reaction, we all know for Haber-Bosch process, N2 and hydrogen and operate form ammonia, it is equilibrium limited reaction. operate 500 degrees C, 250 bar. Okay. So if you do the chemical looping ammonia synthesis, you can do 1 bar. I think 450 to 800 degrees C. Why? So why when you do the chemical looping, you can do the very low the pressure, and then the temperature in a similar range. What's the differences between hydrogen, nitrogen form ammonia, and the chemical looping? This is a circle. I think I want you to take a break and look at it. I'm gonna put this on the screen. Okay, think about my question here. So after this, I want someone answer the question. So look at the loop. The reason you subject to equilibrium because of the hydrogen and nitrogen, they see each other. And then if you put the same amount of hydrogen, nitrogen, they will reach equilibrium under the condition. In chemical looping, hydrogen, nitrogen, they never see each other. You produce ammonia. So that's a hint. And then after this, I will put this on the screen. Half an hour later, I want someone to interpret it based on the combustion oxygen carrier. Now we have this the nitrogen carrier. I want someone who can interpret this, and then why you are not subject to the equilibrium thermodynamics. Okay, let's take a break, and then we'll come back. I think we'll take a 30 minutes break. All right, I'm going to put it on the screen. Think about this yellow highlighted question. Why is not you can do that in 1 bar rather than 250 bar? What's the difference that you do? Okay, all right. Yeah. So, okay, I think that when we come back in 30 minutes, we have a different link, all right? So I'm going to go to that link and then put this on the screen. So then, and then during the break, you guys can talk about it. And then instead of I keep on talking, I want someone who can give a try, interpret this. Okay, let's go. I think we are going to go to different Zoom link. I'm going to post this. Okay. Okay. See you in 30 minutes. Okay.
Yeah.
Half an hour. Right. Thank you.
We'll meet after break, sir. Thank you, sir.
Yeah. Okay. See you. Yeah, we'll meet after break.
Yeah, thank you.